Hello, welcome. Today we're going to be looking at a mass transport example or assignment that is very, very important for our exams. And the question goes this way. A certain process requires a steady supply of compressed air at 600 kilopascal and 50 degrees Celsius at the rate of 0.2 kilogram per second. That is what the process requires. It simply means that no matter what you're doing, make sure you're producing steady supply of compressed air that has 600 kilopascal, 50 degrees Celsius, and 0.2 mass flow rate. That is what you're supposed to produce. So how do you come about? What are you going to do in order for you to get this? Which is what the process that we are talking about needs. This is what is needed. So you're supplying this to a process. So how do you come about this? Now, for this purpose, in order for you to produce compressed air of 600 kilopascal, 50 degrees Celsius, and mass flow rate of 0.2, what do you do? For this purpose, air at ambient condition of 100 kilopascal, air at ambient condition of 100 kilopascal, 20 degrees Celsius is compressed to 600 kilopascal. So it's actually this air that you compress to 600 kilopascal. This one is having more pressure in adiabatic compressor, and then is fed to a heat exchanger. So for you to convert this 100 kilopascal to 600, you have to pass it into an adiabatic compressor. So this is a compressor. So after passing it here, you now feed it into a heat exchanger where it is cool. When you compress, the temperature is high, so you need to cool it down. So to cool it down, you pass it through this heat exchanger as cooling medium. To help cool this air, you need to pass water as cooling medium. Water is used and it enters the heat exchanger at 15 degrees Celsius. So you are passing in water at 15 degrees Celsius and it's leaving at 40. You pass in at 15, leaving at 40. That means it has collected some heat from this air so that it can be at a good temperature. Determine the mass flow rate of water if the rate of work done on the compressor is 44 kilojoule per second. The rate done on this compressor to help it to compress this from 100 to 600 is 44 kilojoule per second. So it's asking us to do what now? To do what? To determine the mass flow rate of water. This water that is going in here, what is the mass flow rate? What's the flow rate it's using in entering? What is the mass flow rate that water is using entering this heat exchanger in order to enable the proper cooling of this? Because when you compress this air, the temperature is going to increase, but you want the temperature to be at 50. So you need to use heat exchanger to take out some heat. So calculate the what? Mass flow rate of the water that is transversing this heat exchanger. That's what you're supposed to do. So with this, you should be able to draw this diagram from what I just explained. This is what is needed because that's what the process, there's a process that is needing this composition of air. So, but this is what the ambient air can give you. So how do you convert what the ambient air can give you into what you need for the process? You need to pass it through a compressor and a heat exchanger. The work of the compressor to compress from 100 kilopascal to 600. Whereas the work of the heat exchanger is to, because it is compressed, the temperature is high, remove some heat from it so that it will still be at 50 degrees Celsius and be coming out with the mass flow rate of 0.2. So this is flow rate 0.2. So with this, what can we do with this? What can we do with this? You understand? So how do we calculate the mass flow rate of the water that is transversing the heat exchanger? So that's what we're going to be doing in the next video. Very, very important. But before we go and before we continue, you need to know that there are some basic assumptions that are made to make this calculation to be simpler. Number one is that we assume a steady state flow, and we also assume that change in kinetic energy and potential energy is very, very negligible. And we also assume that there is no heat lost from this heat exchanger. No heat was lost. apart from the normal heat that the water is getting out from the air. No external heat lost to the environment again. Also, we are now taking that the heat capacity of water to be 4.178, whereas that of air to be 1. So those are the things that we are going to be assuming, and those are the things that we are going to be using to solve for the mass flow rate of water. This is the mass flow rate of air coming out after it has been compressed. What is the mass flow rate that is needed to supply water to do the temperature change that we want in order to have what we need for the process that we are looking at. So that is what we're going to do. So in subsequent class, I'm going to be having this solution. So please take note of how we arrived from this to this and this. Basically, what we are going to be doing here is what we call conservation of mass and energy. You understand? What is coming in is actually what is going out. If what is coming in here should be similar to what the water is taking out. You understand? What is coming in here should be equal to what the water is taking and what is coming out here. So there is no mass loss, conservation of mass, conservation of energy. So put in simple equations of conservation of mass and energy, we solve down. So please, if you like this our video, hit the subscribe button, like, share our video. Thank you. Support us in any way that you can. Thank you and God bless you.